17. The probability the complex assembly line works correctly depends on whether the line worked correctly the last time it was used. That sounds like a transition to me. There's a 0.9 chance that the line will work correctly if it worked correctly the time before, and a 0.8 chance it will work correctly if it did not work correctly the time before. Set up a transition matrix for this situation with state 1 being worked correctly and state 2 being did not work correctly. So they're kind of giving it away and telling you that there are two states. Sometimes they won't give it away so easily, but basically we have to come up with a transition matrix, and I'm going to say it either worked correctly or did not work. So worked correctly, did not work. I think it helps to set it up since it's a two states in the transition as a 2x2 matrix. So they don't give you all 4 entries, but they give you enough. It says there's a 0.9 chance that the line will work correctly if it worked correctly the time before. So we're talking about going from worked correctly to worked correctly is 0.9. The other number they give you is a 0.8 chance that it will work correctly if it did not work correctly the time before. So that's saying going from did not work to worked is 0.8. And that's the only numbers they give you, but that's okay because we know from earlier, we know that these, we know that the rows have to add up to 1. So that means this number has to be a 0.1 in order to make that top row add up to 1. This has to be a 0.2. That's it. 18, what's the long-range probability of ending up in state 2? Okay. Long-range probability of ending up in state 2. Well, I like to come up with an equilibrium vector, okay? Equilibrium vector of long-range probabilities. So basically what I'll do is plug this into my calculator, okay? There are other ways of doing it by hand, but I'm trying to do it fast. So we'll go to matrixcalc.org, and I've got a matrix of 0.3, 0.7, 0.8, 0.2, and I'm going to raise it to a really high power, like 99. I'm going to raise to the power of 99. Any large number will work. This one's 99 is usually pretty good. And so I've got mine going to 8 decimal places. You can have it going to 4. I think 8 is usually pretty good. But when I took that to the 99th power, I get this matrix, okay? And basically what that means is if we started in state 1 or state 2 either way, we're going to have this 0.53 probability of ending up in state 1, and we're going to have a 0.46 probability of ending up in state 2. And so a lot of times you'll write this as a vector, 0.53 repeating and 0.46 repeating. You can change that to a fraction if you want to. I don't really care about that at this point right now. But it only asks you for state 2. It wants the long-range probability of ending up in state 2, and so I only care about this number. That's the state 2 number. And so my long-range probability of ending up in state 2 is 0.46 repeating. Currently, 15% of the population reside in state 1, 30% reside in state 2, and the rest reside in state 3. That's a distribution. That is the initial distribution given usually by x0, and it's talking about how much of the population is in each state right now. So it says 0.15 in state 1 and 30% in state 2. And so that accounts for 45%. There must be 55% left over. That makes 100%. That makes those numbers add up to 1. There must be 55% in state 3. Each year the population changes according to the transition matrix. Here, what percentage of the population will reside in state 2 after 4 years? Okay? Well, we want to know after 4 years. So I want to know the distribution after 4 years. We have a formula for that, and we're going to multiply x0 times the transition to the 4th path, the transition matrix to the 4th path. And so if I'm going to do that, I'm going to go back to my calculator again because I just need to multiply some stuff. X0 was 15, 30, 55. So I'm going to enter in, let's clear that. It was 15, 30, and 55.
and the transition matrix was 0.3, 0.5, 0.2, 0.2, 0.6, 0.2, 0.4, 0.1, 0.5. I just want to check that and make sure that's right. Yeah, that looks right. And so basically, you want to take this matrix over here, this 1 by 3, times this 3 by 3, and we're going to take it to the 4th power. So I'm going to type it in the wrong way and show you that this is not going to work. I'm going to show you something that it's going to give me an error message, and of course it does, because I'm taking the wrong matrix to the 4th power. If you want to take a 1 by 3 and take it to a power, it's not going to work. Of course it's not going to work, because you can only take a square matrix to a power. Basically, I'm just going to switch these around. This is going to make more sense. I'm taking A, which is this 1 by 3, times this, which is a 3 by 3, take it to the 4th power, is going to end up giving me a 1 by 3. So when I multiply these, I don't know that I need 8 decimal places, so I'm going to change it to 4. And I get this answer right here. This is my new distribution. I've got a new distribution here, but this distribution shows me where everyone resides, or the percentage in each of the categories. State 1, State 2, and State 3 after 4 transitions. But it asks me how much will reside in State 2 after 4 years or 4 transitions. And so I only want this one, my answer, 0.4243.